Hi guys, welcome back. This next lecture will be somewhat of the same thing. We'll just kind of refresh a couple things, and I'm going to go through the hazardous weather chapter 2, so we can do a little bit of that. But this one shouldn't be as bad as maybe the first one. So a lot of it will be review. Let's go ahead and share the screen. And we'll go here. So here is your chapter, and we're going chapter 2. And it says from the big picture to your backyard. So the first thing is we have different scales of motion. Things that happen on different sizes, meaning really huge scales to small scales. And then, so that's a spatial, S-P-A-T-I-A-L, spatial scale. There's also temporal, T-E-M-P-O-R-A-L. Spatial is space, how big it is. Temporal means how long does it last? What's the time? Okay, so the first one is called the global scale. Global scale is going to be things that take up thousands of miles. They're going to last for weeks of time. We oftentimes will talk about disturbances in the jet stream as being global scale. Then there's synoptic scale, which is this word here. Synoptic scale would be things you see on a weather map. Areas of high pressure, areas of low pressure. Fronts. They may affect hundreds to 1,000 miles. They may last days of time. So the biggest one is global. Sometimes it's called planetary scale. Then you get synoptic scale. Then you get the next one. This is really the fun one. This is mesoscale. Mesoscale is on the hours of time in terms of temporal resolution. And then in terms of spatial would be maybe tens of miles. So thunderstorms are considered mesoscale. Sea breezes are mesoscale, and I'm telling you guys right now, you got to know those 3 scales of motion. Now there's a fourth one, it's called microscale. Whatever, we're not going to talk about microscale. But global, planetary scale, synoptic, and then mesoscale. So make sure you have those defined really nicely, okay? So the global scale, they're going to give you a little bit about this, and then they go back to the sun. We've already kind of mentioned this. So review time. What's the reason we have weather? The sun differentially heats the earth, unequally heats, because the earth is a sphere. It's more intense over the equatorial regions, the tropical regions. The polar regions are coming in at a lower angle, less intense angle, less radiation coming in. Okay, and it's that difference that's going to set up some flow patterns. Okay, so one of those flow patterns here is called the Hadley cell. So if I go to the Hadley cell and maybe just look at a picture that looks maybe like this, okay? So I'm going to go over here. Oh, I don't want a YouTube video. No, that's not what I wanted. I want a picture. Let's go to this. Where's the picture I want? Just give me the picture. Related images. There. This is much better. Okay, so what we have is over the equator, now they just flatten out the earth. Over the equator, the air is rising, and that's going to cause thunderstorms. And over the poles, the air is sinking. I don't want to buy this, but that's what's going on. So this is notice that this is going from the equator well up to the high latitudes. This one that says Tropic of Cancer, 30 degrees latitude, it's called the tropical Hadley cell. I can get other types of global Hadley cells. Like over here, this one's kind of a fun one. So I'm going to move that picture of me. That's the problem. So the air is rising over the equator, sinking over the poles. Notice this is a global circulation. Rising air is going to be associated with low pressure, which we will see coming up. Sinking air is going to be associated with high pressure. Okay, so we're starting to get into a little bit more weather information, but this is a global scale event. Okay, I just wanted to introduce you that to you. And that's because the equators are warm, the equator's warmer, more incoming than outgoing. The poles are cold, more outgoing than incoming. And then the atmosphere moves and circulates to create that balance. We will definitely talk about why that is. So temperatures, we mentioned temperature is the measure of the average kinetic energy of the molecules. Temperatures go up when more energy is in than out. We've done this before. We did pressure is the weight of the air above you. Sometimes repetition is really important. It decreases exponentially with height. So when we get into the winds, here's some of these winds. I think this is a good one, but again, if I go over here and I look at some of these images, maybe something like this. Oh, the Hadley cell out of Wikipedia. This is great, right? And here's a picture. So what we have is air rises at the equator and sinks at about 30 degrees, and then the air rises at 60 and sinks at the poles. And there's names. This is a polar cell. This is a Ferrel cell. This is the equatorial Hadley cell. You know, we don't need to worry about all of those too much, but I would certainly want you to put in a picture of one of these images. I'm trying to think of what's a really good one. Here's a good one. I like this one. I think this is a really good picture. This one is going to be really good. I mean, there's a whole lot of good pictures in here. But when I look at the wind systems of the planet, okay, here's this image. Well, it's in there someplace. Where are you? I don't want you people. Go out of my life forever. It's not what I want. And I certainly don't want Pinterest. Well, I'm going to go back to here and go picture like this. And notice that the winds are the northeast and the southeast trade winds in the equatorial region. Now, here's something you need to understand right off the bat. We'll get this. You'll get this next week. Winds are named from where they came. Winds are named from where they came. So if I've got northeast winds, they're blowing from the northeast, they blow to the southwest. So they're basically easterly winds, might mean they flow from east to west. Southeasterly in the southern, northeasterly in the northern hemisphere. In the mid-latitudes, the winds are basically westerlies from the west. In the polar areas, they're easterly. And so you can get a lot of these pictures here that show you these winds. Here's another one, right? I'm going to click this one in. I think maybe this will be good. Lots of places you can go, insert an image, and I'm going to be looking for the image to make sure you're doing a good job. Why are you taking so long, huh? Well, again, westerlies, easterlies, northeast, southeast, trade winds, polar easterlies. So we can look at all those. But if you look here, see, there they are, northeast trade winds, southeast trade winds. Trade means persistent. Prevailing means they usually are westerly, and then the polar easterly. So that's just something important that you understand this. Upper level winds in the mid latitudes is going to be strong winds. They're usually what we call the jet stream, and they're going to be up at the end of the troposphere. Now, do you remember what that was called? Yeah, that's called the tropopause. So the winds are strongest way up high, and they're blowing from west to east, generally speaking. In fact, let me show you an example of what I mean by that by looking at one of the models that we use in our study of the weather. And I'm going to go up to 250 millibars. That's about where the jet stream is going to be located. And here is the jet stream winds blowing basically this way. Okay, notice they're wavy. Those are waves. Those are called long waves. These are all basically global scale waves. But if you notice that they're basically blowing from west to east, and that's what the jet stream is going to do, especially in the mid-latitudes. So we use this type of stuff all the time to really try to figure out what the weather is going to be and how to forecast that. So there's just the jet stream. And I think there's going to be some things go a little bit more detail about the jet stream. I'm not going to go into here too much at this point during this lecture, but look at the moisture on here. Make sure you know what these terms mean. Evaporation or condensation, I think that makes sense. Transpiration is water vapor entering the air through plants. So all of these things we're going to be getting into in a lot of detail throughout this semester. Topography is just the study of mountains, and we've got rain shadow deserts close to valleys or mountains, and we're going to be talking about flow, and that makes the air travel in different speeds and directions. We're going to be talking about climate. This is just a brief introduction to things that we're going to get into in more detail. For now, just say climate is a 30-year average. I think that's on your worksheet too. So we've got these big, long-term global patterns like El Nino you probably have heard of. So global scale summary, that's just the big picture. Now there's some in here, the review questions, and this is where I want you to start taking the review questions, finding the answer, and putting the review questions into your notes. Okay, so I'm not going to give them to you now, but go ahead, copy and paste them. The answer is going to be given to you. Try to answer that on your own. This is how you learn, by thinking and then seeing afterward. And just try those on out there, okay? Now, there's a word in here I want to look at. It's about pressure gradient. So define the word gradient. A gradient is a change of something over a distance. So we can have pressure gradients, which says the pressure over here is different than the pressure over here. That difference as I move over a distance. Now, sometimes I move up. So I have a pressure gradient going up and down. That's what we call a vertical pressure gradient or a horizontal pressure gradient. So it's a change in the pressure as I go from here to there over a distance. Make sure you know what a gradient is. That will help you as you read in upcoming lectures and modules. So add those questions, go through them, and that'll be really good. Now, synoptic scale is going to be things you see on the weather map. So I've got highs, which we call anticyclones, and lows, which we call cyclones. Okay? Over here, the first thing that I want to talk about is air masses. Okay, so air masses are going to be areas of air with certain characteristics. And the two most important characteristics are whether they're warm or cold, the temperature, or whether they've got a lot of moisture, or they're dry, which is something we'll call the dew point, but we'll get to that later. So if we start over water, do you agree that's probably going to have more water vapor in the air? Water vapor is invisible. So that's called maritime. If it starts over land, it's called continental. So continental is going to be drier than maritime. P stands for polar, so that's polar air masses. And then T stands for tropical, that's going to be warm. So polar is cold, tropical is warm. So I've got CP, continental polar, that's cold and dry air coming in from Canada. I've got MP, maritime polar, that's cold but moist air. I've got maritime tropical, that's warm, moist air. We get it from the Gulf of Mexico. When it's a hot, humid day, that's maritime tropical air. And then we got continental tropical. In Chicago, we don't get continental tropical very often. That's more if you go out to Arizona, New Mexico, Old Mexico, where you start to see that. Now there is one that's even colder, way up, very, very high. It's called continental Arctic. So here's your 5 air masses. What's the coldest air mass? Write this down, continental Arctic. That'll be on a test. I'll ask you these. What I would suggest you do is go air masses and add a graphic of air masses. This is probably the most common one, where it kind of tells you where they come from. This one doesn't have the continental Arctic that this one does, so maybe this is a better image. So find an image, put it into your document, and then you have all the stuff. If I say, what kind of air comes from over Canada? I hope you know where Canada is. And you'd say continental polar. What's the coldest? Continental Arctic. What comes from moist air from the Gulf of Mexico? Oh, maritime tropical, right? It's very easy to understand that. It's not so bad. I think you're going to be fine. Okay, now we have fronts. And I want you to define what a front is. A front is a narrow transition zone between two different air masses. So I have a continental polar and I have a maritime tropical. Those are two air masses. They change properties, temperature and moisture content, over a short distance, and that distance is what we call the front. So it's a strong gradient of temperature or a strong moisture gradient. So it says right over here, that's what a front is. Now there's 4 types of front where you should probably write this down. You get a cold front, you get a warm front. There's no such thing as a hot front. There's no such thing as a cool front. It's cold front, warm front. Don't ask me why, it just is. We also have a stationary front. And then the fourth one is called occluded, O-C-C-L-U-D-E-D. I'm not going to worry about occluded fronts in this class. But the cold front, and this is important, is the leading edge of cold air mass. So it's the leading edge of cold air mass. And I want you to look at the video. So you should, when I give you these lectures, you should always have this module up as well so you can do things like I'm asking you, okay? So watch this. Notice cold air, and you should write this down. Cold air is more dense than warm air. So that density is about how much mass is in a certain amount of volume. Something, if you put a lot of people in a small room, it's high density, right? COVID-19 world, we have to spread out the density, right? We have to separate people, so that's going to be low density. Air does the same thing. The molecules are really close together, and it's cold, and when it's warm, they're less together. Well, if I had a balloon that's helium, helium is less dense than the surrounding air, and therefore the helium balloon will go up. It's less dense, and when it's less dense, we say it's buoyant. B-U-O-Y-A-N-T, buoyant, buoyant. Now, warm air is less dense than cold air, and therefore warm air surrounded by cold air will be buoyant. So when the cold air starts to advance, as you see in this picture, that cold air wants to stay close to the ground, and the warm air is lifted above it. So what we're going to say is that fronts provide lift. They force warm air to go up, and the cold air comes down. So important. So when cold air advances, it's called a cold front. You're outside, it's really nice, all of a sudden you see this, all of a sudden the winds change direction, it gets really cold, that's a cold front that's just gone by. So now you would think, well, it's a warm front, warm air advancing, and the answer is no. Because if this warm air advanced, it's going to go up, and it's not going to displace the cold air. So they say it's the edge of advancing warm air. That's bad, okay? Do not say this. Warm front is where cold air retreats. It's the trailing edge of cold air. Because if the warm air is advancing and the cold air is just hanging there, the warm air is going to go over it. Guess what kind of a front that would be? That stationary front. If the cold air advances, it's a cold front. If the cold air retreats, that's a warm front. It lets that warmer, less buoyant air, or more buoyant, less dense air, take over. Okay, so a cold front is advancing cold air. A warm front is retreating cold air. A cold front is the leading edge of cold air. The warm front is the trailing edge of cold air. In both circumstances, warm air is lifted. If the cold air doesn't move, then we have a stationary front. And then the occluded front, I'm not going to worry about that for now. Synoptic scale, we talk about areas of high pressure and areas of low pressure. Here's a weather map. The pressure here is 985 millibars. The pressure here is 1,016 millibars. Lower pressure, higher pressure. The difference in pressure, that creates a gradient. Okay? So we're going to talk about what these things are. And this is where it's going to get a little bit more complicated as we go into next week. For now, I want you to cut and paste or redraw this chart into your notes because this is so important. An area of low pressure is surrounded by higher pressure, right? And the opposite is true. We call this a cyclone. An area of low pressure is a cyclone. An area of high pressure is an anticyclone. Now, it says often produces cloudy skies and precipitation. So I'm going to give you basic, super basic weather. To get precipitation, I need moisture and I need air to rise. And that will become super important as to why this happens. But the simple way to explain weather is if I have moisture in the air and the air is forced to go up or it goes up, then I get a chance for precipitation. I certainly get clouds. When air sinks, which we call subsidence, S-U-B-S-I-D-E-N-C-E. Subsidence is just a vocabulary word that you need to put into your brain, because if I use it, I'm not going to define it every time. Subsidence means sinking air. Okay? So when air rises, it produces cloud and precipitation. When air sinks, this air is going to clear up, and high pressure usually means nice weather. If I told you, hey, next week I've got an area of low pressure coming in, you should know that means bad weather. High pressure coming in means clear weather. This is going to be foundational to everything we do in the FEMA test, so make sure you understand that. Now, it's a cyclone means the air is cyclonically moving. Cyclonically in the northern hemisphere means counterclockwise. Technically, cyclonic means the way the Earth rotates. So if the Earth is rotating and you look down at the North Pole, you'll see it going counterclockwise. And that's what cyclonic means. Southern hemisphere, if you look up at the South Pole, it's going clockwise. So cyclonic, southern hemisphere. Now, just so you know, I will never ask you in class, I won't even talk about southern hemisphere stuff. So in your mind, I'm okay if you go cyclone, cyclonic means counterclockwise. Air around the low pressure moves cyclonically, and in the center, air goes up. Okay? Opposite is true of high pressure. Air moves clockwise, and it sinks, subsidence. Now, it says the right-hand rule. So if you look at your hand here, okay, and you go, hey, move my fingers like this, curl my fingers. Notice that my fingers, when I look down at it, curl counterclockwise. That's cyclonically. And the air is rising. High pressure is the opposite. So if you just want to remember that, the little right-hand rule tells you how the air is moving. And this will be important. Okay. Now here's a whole bunch of maps and isobars. Take a look through this, read it. I think there might be some questions on it. I'm not going to go through it too much. Now, we are going to get into this in more detail later. We can talk about moisture. And remember, we're talking about maritime air masses that have the moisture. Eventually, we are going to be talking about how we get clouds to form. If the cloud becomes big enough, we get precipitation. Now, these are all things we're going to get into in more detail, but it's something you ought to go through on your own to finish up this module. And we're going to talk about humidity and the sling psychrometer and the dew point. But we're going to talk about lift. So what I want to do is talk about something simple right now, which we're going to re-emphasize and reiterate as time goes on. We're going to talk about a parcel of air, a box of air. Okay, it's called a parcel, P-A-R-C-E-L. So we've got this little box of air. It's just an imaginary container. In my other classes, I call it a Vegas box, because what's in it is in it, and what's not in it is not in it. So just imagine I have a box in my hands. There's your box. Now inside there's molecules moving around, and they're hitting the inside walls of the box. Well, that hitting, that force, is what we call pressure. It's exerting pressure on the inside. Well, what about outside? Air pressure is molecules are trying to get in the box. That's pressure from outside. So this box, made of imagination, and this is where it starts to become really significant, is that the pressure inside that box is always the same as the pressure outside the box. The pressure inside the box is equal to the pressure outside the box always. So imagine that I take the box, the parcel, and I lift it up. What's the pressure doing outside? Well, air pressure is the weight of the air above you, so the pressure goes down. But the pressure inside has to be the same as it is outside, and the pressure outside went down, so what's the pressure inside doing? Answer, it's going down too. How does the pressure go down? The box expands. So, and you're going to need to pause me and write this down and circle it and put a box around it and highlight it and all sorts of stuff. When I take air, parcel of air, and I lift the air, the first thing that happens to it is the pressure decreases. First thing that happens is the pressure decreases. The second thing that happens to it is the air expands. Okay? I hope that makes sense to you. Anytime I say, what happens when air goes up? What happens when I lift air? First thing that happens is the pressure decreases. And I'm going to ask you this on a test. What's the first thing that happens? And you say, the pressure decreases. Are you getting me? This is on your test. So what's the second thing? The box expands and cools. I'm sorry, the box expands. That's the second thing. I gave you the third thing. Do you know what else it does? It cools. And that's the weird thing. And this is so important that you understand what I'm about to tell you here. Air is lifted up, the pressure goes down, the box expands, and that expansion results in cooling. Now that kind of cooling is called adiabatic cooling. Okay, so that's what's happening here is we have adiabatic cooling. Adiabatic, you need to say that word out loud. Like 79, the next number is 80, adiabatic. So when the air expands, it's gonna cool. You're not adding heat to it. Remember we talked about heat coming in or heat going out? Adiabatic means there's no heat, there's no radiation, there's no conduction, there's no convection. The air is expanding and it gets cooler. Do you know what it gets cooler at? Something called the dry adiabatic lapse rate. Remember what a lapse rate is? Which is 10 degrees Celsius per kilometer. Dry adiabatic lapse rate. Don't worry about dry, it just means we don't have a cloud yet. Adiabatic means I'm not adding heat, it's just expanding and getting cooler, and it's getting cooler at a rate, 10 degrees Celsius for every 1 kilometer I go up. So anytime air goes up, it's going to get cooler. Eventually the water will condense, which we'll get into later on. Right now you have to understand, air rising causes cooling, and to get clouds, I need cooling. If I have air sinking, what do you think is happening? If air comes down, it's going to get to higher pressure. It's going to be the opposite of expand. It's going to get compressed, and it's going to get warmer by 10 degrees Celsius per kilometer at the dry adiabatic lapse rate. Ask me if that's important. You don't have to ask. It is super important. So fronts provide lift. We're going to talk about other ways to get air up as well. But there's your synoptic scale stuff, and they talk about a dry line. Don't worry about that too much. There's a warm front, a little red line with half circles, blue line with little triangles is a cold front. Here's some more questions. I would answer these questions also. Get to the practice of trying these questions. Make sure you know the answer and then find out if you were right. Test yourself. It'll help. Now the last scale is the mesoscale. Okay, mesoscale is much smaller. Storms, temperature, all those things are providing all these lift. We're not going to get into that right now. That'll be as we come forward in time. So we actually look at lifts as providing, or fronts as providing lift. Those are actually mesoscale in the lifting, but don't worry about that. What I do want to do is this. So I'm going to go over here, and I'm going to use my little whiteboard, and I'm going to create a little tube there and there. That's kind of close to what I want. And I'm going to draw a little cylinder. And you know what's in the cylinder? Water. So I've got some water in that cylinder. And you know what I have on the top of the cylinder? I have a couple of holes up here. And I got a couple of holes down here. Okay? Now, I want you to imagine that I'm putting water into this cylinder down here. Okay? Notice the way my arrows are pointing toward the middle. That's called convergence. So the air is convergent. So I'm going to write that down here so you have a nice little example of what I want. Convergence. Now, if I do that, what do you think's happening up here at these holes? Do you agree that the water is probably coming out of those holes? Right? So what do you think that's called up there? Divergence. So I got divergence up there and convergence down here. Okay? Now, I'm going to skip over here. You can still see that diagram. You get the idea of what do you think is going on in the middle? If I'm pumping water in down low and you see what I did? It goes up high. So what's happening in the middle is we get air, or fluid that's going to move up. Okay? So when I've got convergence at low levels, I have to have divergence at upper levels, and the fluid, the water in this case, moves up. Same is true in the atmosphere. Okay, what is this called? What is this concept? This concept is so important. It's called mass continuity. In words, and I'm going to quote this, not type it, mass continuity says, when I have a level of convergence in the atmosphere, I also have a level of divergence in the atmosphere and vertical motion in between. Low level convergence, upper level divergence, and then air, or in this case water, goes up. Now if I reverse the arrows and made them turn the opposite way, do you agree they're convergent aloft and sinking air, and then divergence at the surface? So which kind gets me clouds? Rising air. So whenever I've got convergence at the surface, that's going to force the air to rise. And what happens when air rises? The pressure drops, the air expands, and the temperature drops by 10 degrees Celsius per kilometer, which is called the dry adiabatic lapse rate. You better pause and make sure you know what I just said, because I'm going to say that all the time. That's mass continuity. All right, beautiful. Notice this area of low pressure here. I'll go back to my little colored pencil. I don't need to have this big. Notice that the air is sort of spiraling into this. Do you agree that the air is converging in an area of low pressure, and that convergence is going to result in air ascending, and then somewhere up here it's got to diverge. That's mass continuity. So now do you see why low pressure means rising air and we get clouds and precipitation? Convection, we're not going to talk about this quite yet. Oh, diurnal variation. We get these ideas. We get lifting along terrain, or what we call orographic lift. So mountains, air going up a mountain. And we're going to see this in next week with the wind systems. Air goes up mountains during the day and down slope at night. Goes up valley during the day, down valley at night. Dry lines are just differences, not worried about that. We're talking about instability. This is stuff that's going to come on. We talked about an inversion. So this is all stuff that you should be reading. We're not going to get into much more detail at this point. I'm not going to worry about this. Here's something that we're going to eventually know, something called CAPE, convective available potential energy. Just kind of get that into your mind now. We'll talk about it later. And then we talk about the local weather, and it says, oh, what's happening, and blah, blah, blah. And there's a little summary. So a tornado or a thunderstorm is going to be mesoscale. And there's your questions for mesoscale. So do those as well, okay? And then you go all the way through there and you think, wow, are we done? And we're kind of done with that page of weather. That's not bad, huh? So we're going to have to learn a lot because there's more important things that we're going to get into more detail with the modules next time. But for now, just understand mass continuity is important. We need to understand that I take air, and when I lift air, the pressure goes down, the air expands, and the temperature drops. It cools. Dry adiabatically at 10 degrees Celsius per kilometer. And I really shouldn't do these lectures when my neighbors are using a leaf blower or their lawnmower, which is annoying. I don't know if you can hear that, but I can. Anyway, I'm done. You're done with the lectures for this week. You can move on to next week now. Finish up all of the stuff that you have to do, and I hope all is good. If you have any questions, what do? Message board, or you may text me. But for now, have a great day. I'm going to stop sharing and say goodbye.